Welcome to the course on plasma physics and application to fusion energy, astrophysics and industry. My name is Duccio Testa, and in this lecture we will be studying the stability of the MHD equilibrium. What happens if a plasma in MHD equilibrium is perturbed? We want to answer this question, and we will do this by working through some examples of MHD instability. We will be looking at the sausage instability, at the kink instability, and then at the Rayleigh-Taylor instability. We will then look at the effect of the wall surrounding the plasma on instabilities and the link to the flux freezing. And then we will study method to analyze the stability of MHD equilibrium. So what happens if a plasma in MHD equilibrium is perturbed? There are different possible scenarios, and we will look at them in analogy with classical mechanics. The first example is this one here. We have a potential well, the black line, and our system, the green dot, sits at the bottom of the potential well. This is a situation of stable equilibrium because if we displace our system, its potential energy increases, and then it will roll back to the bottom of the well in its starting equilibrium position. So this is a stable situation. The second example is actually the opposite of the first. We are in a situation of unstable equilibrium. In fact, we are at the top of the hill in the potential energy. So if our system is displaced, its potential energy will decrease and it will keep rolling away from the equilibrium point at the top of the hill. This is a situation of unstable equilibrium. We have a third situation here where the equilibrium of our system is indifferent because the potential energy is flat. So we can move it left or right. Potential energy doesn't change. So this is a situation of indifferent equilibrium. The situation can actually be more complex. For instance, we have a case here where our system sits at the top of the hill in a potential energy, but in fact we notice if our equilibrium is perturbed, the system will roll down the hill and it actually will not go very far because it will drop at the bottom of a potential well here. And this is another situation of equilibrium. So this system is really linearly unstable, but in the end it will be non-linearly stable. The final case here is the opposite of our previous case. The system is in initial condition of equilibrium, it's at the bottom of a potential well, but if we move it, it may go up to the top of the hill, then potential energy decreases by rolling down the hill. So this system is linearly stable, but non-linearly unstable. We will consider example of instability affecting the MHD equilibrium, and therefore we will basically work on situation where we are in this condition, situation of unstable equilibrium. The first example of instability is the sausage instability in the Z-pinch. Remember from previous lecture, the Z-pinch is a confinement device where we have an axial current, Jz, and an azimuthal magnetic field, B theta. The equilibrium of the Z-pinch is described by the balance between the gradient in the plasma pressure P, the magnetic field pressure B squared theta over 2 mu naught, and the tension of the magnetic field lines being wrapped around the surface of the Z-pinch. Now we assume an initial perturbation in the form of compressions and bulges. P1 is a point where we have compressed the plasma. The total current in the Z-pinch, I, remains constant. At this compression point, the radius of the plasma cross-section becomes smaller, and therefore B theta increases. So the magnetic pressure increases, which squeezes the plasma further. So we are further compressing the plasma. The initial perturbation grows. Basically, at the point P2, which is a point of bulging, we have the opposite B theta decreases, which then allows the plasma to expand further. So the initial perturbation grows, and the net effect is the sausage instability. Now, the second example of the instability is the kink instability in the Z pinch. We assume an initial perturbation in the form of bending. We've pushed up the plasma. At P1, the field line come closer to each other. B theta increases. Therefore, the magnetic pressure increases. And this pushes the plasma up. At P2, the field line comes apart, B theta decreases, the magnetic pressure decreases, and the plasma cannot be pushed back down. So the net effect is the growth of the initial perturbation. The plasma is pushed up. The net effect is the kink instability. A third example of instability is the Rayleigh-Taylor instability in plasmas. We consider an equilibrium with the plasma on top of a vacuum region, subject to gravity. The interface between the plasma and the vacuum is perturbed by a ripple. There is a drift that is induced by the gravity, and this drift leads to charge separation. Ions on one side, electron on the other side. Charge separation leads to an electric field E, and the resulting E cross B drift increases the original perturbation. It pulls the ripple down, it pulls the ripple up. So again, the initial perturbation grows. We are in a situation of instability. If we reverse this situation, so if we put the vacuum region on top, or if the direction of G is reversed, this equilibrium becomes stable. Now, the most common example of Rayleigh-Taylor instability is the Rayleigh-Taylor instability in fluids. Here we have a simulation that shows the development of the Rayleigh-Taylor instability when we have a heavy liquid, water, in blue, that sits on top of a light liquid, oil, in yellow, subject to gravity. We have an initial ripple at the interface surface, and we see that as function of time, this ripple is amplified. We can go back to the Rayleigh-Taylor instability in plasma, and the centrifugal force due to the magnetic field curvature plays the role of gravity. This force, Fc, is expressed by this formula, and you see that it depends on Rc. This is the radius of curvature of the magnetic field line. Here we have two drawings. In the first case, Rc points away from the plasma. So it goes from the heavier fluid to the light fluid. This leads to instability. In fact, this is a situation that we call situation where the magnetic field has a bad curvature. The magnetic field is concave towards the plasma. The opposite situation is if Rc points towards the plasma, so from the lighter fluid, the vacuum, to the heavier fluid, the plasma. In this case, the equilibrium is stable, and this is a region of good curvature. The magnetic field is convex towards the plasma. Now let's look at the role of the wall surrounding the plasma on MHD instability. You consider a plasma column which has a current J and a magnetic field B. There is an instability that develops and pushes the plasma towards the surrounding ideal wall. The resistivity of the wall, eta, is 0. The magnetic field cannot penetrate into the wall. So we ask ourselves, can the magnetic field penetrate inside the plasma, and can the magnetic flux through the plasma change? To answer this question, we have to study one important property of ideal MHD, which is the conservation of the magnetic flux. The magnetic flux phi is the flux of the magnetic field B through the surface S that encloses the field line. These are our field line. This is the surface S, which is delimited by a contour C. So let's describe the time derivative of the magnetic flux, dφ by dt. We can put the time derivative into the surface integral because the temporal and spatial coordinates are independent. So dφ by dt is the sum of two terms, the time derivative of the magnetic field, dB by dt dot ds, plus b dot the time derivative of ds, the surface element. We can study these two terms separately. We can start with the first one, and we can use Faraday's law. So we have that the integral over the surface S of dB by dt is minus the integral over the surface S of the curl of E dot ds. We can now use Stokes' theorem and express this surface integral in an integral over the contour C delimiting the surface. Now we can work on to the second term. So we are looking at the time derivative of the surface element ds. So at time t1, the surface element is delimited by this contour C, which moves at time t2 to a different contour C2. So if we take a point on the first contour, we can have the vector dl and then the normal, and so the variation of the surface element ds, we can simply see that it is the cross product of v dt cross dl. So we can use this expression for ds into the second term of our integral. So our surface integral b dot d by dt of ds becomes the integral of the contour C of b dot v cross dl. We can now put the two terms together that we have obtained for the time derivative of the magnetic flux dφ by dt. So we have two integrals over the contour C. We can rearrange the terms into the second integral and combine it with the first. What we have here is that dφ by dt is minus the integral over the contour C of E plus V cross B dot del. But this is the Ohm's law, and we know that E plus V cross B in ideal MHD is equal to 0. And so this integral is equal to 0, which tells us that dφ by dt is equal to 0. As dφ by dt is equal to 0 in ideal MHD, the magnetic flux through every surface moving with the plasma is constant. The magnetic flux is therefore frozen into the plasma in the absence of plasma resistivity. We can now go back to the effect of the wall on MHD instabilities. The magnetic field, when the plasma is pushed towards the wall, cannot penetrate into the wall, so the magnetic field is compressed in the vacuum region between the plasma and the wall. The magnetic pressure is increased, and that pushes the plasma back towards the center of the device. This tells us the plasmas can be stabilized by a surrounding wall. However, this effect is limited by the finite resistivity of the plasma and of the wall, and so this effect only lasts over a finite time scale. Now let's look at some general methods for the analysis of MHD stability. For uniform plasmas, we can perform a Fourier analysis in space and times. This corresponds to a normal mode analysis. So we assume perturbation in the form of an exponential I k dot x minus I omega t, and then we look at the imaginary part of omega, the wave frequency. If the imaginary part of omega is positive, we are in a situation where the perturbation grows, and so we are in a situation where an instability develops. For non-uniform plasmas, we can cast the MHD equations into a force balance equation you have the mass density of the fluid element ρm times d2 psi by dt square. Psi is a fluid displacement, and this is equal to a force operator F of psi that represents the force acted on the fluid element whose mass density is ρm, producing a displacement psi. We can then perform a Fourier analysis only in time. This tells us that minus ρm omega square psi is equal F. This is an eigenvalue equation. The sign of omega square determines the stability or instability. We can also perform an energy principle analysis. We can evaluate the equivalent of the work delta W, which is minus 1/2 the integral over the plasma volume V of F dot psi. This corresponds to the change in the potential energy of the system. The sign of delta W corresponds to stability or instability. Now, we've seen that the plasma in an MHD equilibrium and in general can be subject to many instabilities. How can we control this instability? We have two methods. The first method is a passive control system. We use intrinsic stabilization mechanism, as we have seen in the case of a wall surrounding the plasma. The second method is an active control system. We detect the onset of an instability and apply feedback control schemes in real time that act on plasma parameters, and with this feedback control scheme we can try to stabilize the instability or limit its development. Now let's summarize what we have discussed in this lecture. We have qualitatively discussed some examples of instability: the sausage, the kink, and the Rayleigh-Taylor. We have seen that the wall surrounding the plasma can be stabilizing because of the frozen-in condition of the magnetic field, which is valid in ideal MHD. And then we have seen that the linear stability of a MHD equilibrium can be studied using Fourier analysis techniques or energy considerations.